Don't know. You know as much about this as I do. So the only time I played around with it is this weekend, uh, and I didn't have students to tell me what they actually saw. So proximity sensors. What do we mean by proximity? Yeah. So what we're looking at proximity sensors is we're going to look for the device to be at a spot. One position. So the position sensors that we looked at before, these were position sensors. We could tell if it was at a position over a range of positions, right? Okay, by that. This is going to look for whatever we're trying to detect it when it's at a certain spot. Oh, I'm sorry. I stopped sharing. I might have to remember to do that too, so y'all have to let me know. There now, right? Okay. So hopefully before the end of the semester we'll know what a sensor is, right? And of course we looked at position. Is that all the position sensors? No. At your plant you might run into more, but at least now what they did, what they do. We covered the most popular. We covered all of them that y'all got at y'all's plant, by the way, right? We're okay there. Next time we're going to look at, of course, is proximity, which is where we're going to tell if the position is at a certain spot. So proximity sensitivity at a certain place. Limit switches are technically not proximity sensors, but they have their own name. So limit switches were the first proximity sensors that we actually used in automated control systems. So they have their own name. All the other ones we call proximity. And usually, when we talk about proximity, we usually indicate that it's some type of solid state, even though there's two in this. There's one in this list that's not. And that's the magnetic reed that we use all over. So we're going to look at limit switches. We're going to look at optical proximity sensors, magnetic reed switches, Hall effect proximity, magnetoresistive proximity sensors, capacitive and inductive. Okay. So of course, push buttons would be proximity sensors because they tell when you're at a certain spot, right? We don't call them proximity sensors. We call them push buttons, so they have their name. So you can't turn off or on the push button all across the room. You got to be at a certain spot to get there, right? You understand that? Now these things we have two types. So we have normally open and normally closed. Well, this is a selector switch. And these are selector switches. And there's a selector switch over there. And then these right here are push buttons. These right here are E-stops. And these will be what we call normally closed. Now, what do we mean by normally closed? And we should have normally open. Yeah, so their unenergized state would be they open the circuit, right? You understand that? Whatever, no current flow would get through it. So normally closed means it's always got a path for current flow to get through. Normally open means there's not a path until you actuate it with whatever actuator you use. Your stop buttons are always normally closed. Some of them have latching positions on them, which means when you hit them, they'll stay in their stop position until you either pull them out like ours does. But a lot of them actually have a second feature on there, which means not only do you got to push it in a little bit and then do a rotate them and then pull them out. Just make sure you don't accidentally pull those out. So electric switches usually has 2 or 3 positions. In the industry, we want these things to be big because what we're trying to do is trying to get it capability so people operate them in gloves, right? A limit switch. This is an electromechanical device. So right off the bat, we know this can fail in 2 different places, 2 different ways. It could fail, electrically or mechanically. Most mechanical failures are due by people that don't mount them right, that people that don't put motors on there. These are pretty reliable and they last pretty while. We can have problems with that. Must make physical contact with the object it's trying to measure. Now, the operator is types of limit switches. We have rotary switches, which the actual operator moves in an arc. And then we have plunger type where the actual operator moves in and out, right? Okay. These usually have a spring in them that returns them to their normal position when they're not being actuated. These things don't have any contacts in them, 1 or 2 contacts. Usually it has, most of them will either have a normally open or a normally closed, or they'll have a single pole double throw. There, which will have 1 normally closed connected to 1 normally open, right? The device that makes physical contact with the object and causes the limit switch to contact change states. We have rollers, we have rods, we have loops, we have springs, we have different types. We have 2 categories. We have pilot duties. Some people call these heavy duties. These guys are big. They are designed to run loads. So we can have these guys here directly energizing inside 3 days and all kinds of stuff. We don't run into a lot of these in PLCs anymore because PLCs don't require a lot of current to operate. Right? We have what we call electronic duty, also called precision. These are small in size. They're designed to switch low voltage and currents. Used in electronics or PLC control systems, usually has only 1 contact, single pole, single throw, or single pole, double throw. 1 or, are we okay? Yes, no. So these are examples of limit switches. These are heavy duty, or pilot duty. We got 1. Some of them, by the way, you can actually change this head out. It looks like this one gives us that ability. And then you could change it from a rotary operator over to a plunger operator. The one that we have, in fact, we can pass one of these around. I don't know if we got both types or not, but and we got several of these, and you can actually look at the contacts inside these. They got a lever system inside there, so when it hits a plateau, it switches real fast. Why do we want contacts to switch real fast? So they won't arc and weld together, right? Are we okay? These are examples of electronic duty. They're very, very small. They still do exactly the same job. They're not designed to run loads, but they very easily can bring an input into a programmable controller, and then let the programmable controller provide an output that brings in relays to the load. So on our manufacturer line, we have several of these over there on 4 different types of things. What advantage does a limit switch have over a solid state limit switch? What would you think? Well, they got to switch power. We don't have to power them up to make it work. They turn the switch power. Okay, so that'd be one advantage, right? I'm gonna put that note. Some switches are electromechanical, so they cost a lot less than its counterpart. These solid state limit switches are not very cheap. Technically, these are proximity sensors, but we don't call them proximity sensors. We call them limit switches. They're used for all type of applications now besides just finding limits, right? You understand that? So originally, that's what they were used for, like in mill machines and stuff like that, where the carriage would move, and when you hit a limit, it would automatically do what, reverse, and that kind of stuff. And that's how they got their name. We use these guys to count. We use them for position to see if something's in the right position or not. Yeah, we got one over the on the Festo line that senses if the spring is available. So that's not a limit, right? Understand that's their names. Then we move into what we call non-contact sensors, referred to as proximity sensors. These are usually going to be solid state, not always. Now, what advantage does solid state or electronic sensors have over electromechanical sensors? Non-contact means we don't have to touch or sense it, right? So that's a big advantage. Not getting pitted out of these little limit switches are constantly getting whacked on, pushed around, bopped around, right? You understand that? The other advantage we have, of course, is that they're electronic. They're not electromechanical. Electromechanical devices can fail two different ways. They can fail what? Mechanically and electrically. These guys can only fail electronically. Well, they can fail mechanically. I've seen when people mount these things wrong. And then an object comes by and does what? It wipes it out. But they themselves, so they don't know. No physical contact with items being sensed. So this is not exactly true because one of them, a lot of people, the book, and by the way, out there on the Blackboard site already is all the labs that we're going to use. So a lot of the information that we're getting in this class, or we're going to use in this class, if I can find it, actually comes from right here where it says, course content. And then labs. And then these are the actual, and every one of these, when we load them in, and these are very similar to the labs that we did in motor controls. So it starts off with what? So what this does, it starts off with a supplement. And the supplement basically is the very first that tells you a bunch of information about what we're going to be dealing with, right? About different types of liquid level. This is just about the different ways we can use them. So this is going to be one of my main sources for questions on test. And then of course we have the actual labs. I'll give these out to you. I'll give the labs out to you, but the actual what? The actual this part right here, you'll access that online. Everybody okay? That makes sense? And what I've done this time, by the way, is I've put the lab chapter quizzes online. So those that y'all had to attach at the very last lab on motor controls, here you won't have to do that. So at the end of every lab, you'll come and do your lab chapter quizzes right here. Now, what the advantage of this is you get 3 shots at making the best grade. How many did you get? One shot, right? And then, of course, here, automatically graded. that's most of my work is doing what the lab they grade as we go through. And then all I do when you turn them in is make sure you get lab questions out there. And then I had to go back and grade all these guys. So that's up there. By the way, these are all being keyed in. So when you do any of these and you see any errors, you need to text me or email me and let me know, because like I said, every bit of this stuff had to be keyed in, these quizzes. So what we might do, it depends on how long this thing lasts. I know we're all out on spring break next week, and this has kind of put a damper on our spring break. But we might even have y'all do the lab quizzes and everything as we advance through the thing. Depends on how long we're out. So far, the date we've been given would be after spring break. We'll have to look and see what they're going to do then. So basic stuff. Most solid-state electronic sensors only provide a single pole, single throw, or single pole, double throw simulated contact. So we don't actually have a contact in our solid-state sensors. They either use transistors to switch them things on or off, or they use triacs or SCRs or some electronic device that switches these things off. Usually that's transparent to you, because all you're looking for is that contact to do a close or a contact open. So either the contact that's current through or the contact does not get through. But you're not going to hear a click like we do on relays, right? You're not going to hear that click that tells you that it's operating. A lot of them will put a little LED on the side, which is pretty neat. That'll light up when it triggers and allows something to come through. What we have to realize is these guys will always drop a voltage across because they're not real contacts, they're electronic devices. Two-wire either is not required, it does not require it, either is not, it does not. Either does not require a separate power supply connection. It powers through the load. So these guys, these wire sensors that are solid state, don't drop a pretty good deal of voltage. I think ours, when we finally get to the lab, that's one of the things you're going to measure on our two-wire sensors. We're going to do a two-wire sensor. If the sensor do sense, they'll drop about between 4 and 6 volts. But these are going to be high voltage sources, right? Understand? So you can afford to have that voltage drop. You could not afford to have it 4 volts, 6 volts drop in a solid state. You're running up to 24 volts, right? Okay. That's quite a bit different. So then we'll move to a 3-wire sensor. A 3-wire sensor only provides one contact, and a 4-wire sensor that has to be powered will require provide a double pole. That's wrong too. It'll provide a single pole double throw contact. Okay. Makes sense. There's a question so far. Anybody remember the color code? We've already talked about this on this class. So this guy right here on a 2-wire sensor, brown is going to point toward L1, and then blue is going to point toward L2. And the load's going to be in between that, right? On a 3-wire sensor, Then brown is going to connect to plus DC. So these are DC sensors. Blue is going to connect to the minus on your DC power supply, and then black is going to be the signal. And this is going to be the black is going to be a normally open, simulate a normally open contact. Okay, correct. A 4-wire sensor, what's going to point toward plus? Brown. What's going to point toward, what's going to connect to the minus? Blue. Then your black is going to be a normally open, it's going to be simulate a normally open contact, and then we'll add another one, which will be a white, which is going to be a normally closed contact. So these are going to be single pole double throw. Are we okay? So the first one we'll look at is your photoelectric sensors. These are used a lot. You know what the biggest complaint we have about these? You have to keep them clean. So they'll get any industry I've ever been in, except for making. So these are different methods we can use. These are the same thing. So here we're using this to look like count batteries or something. So what happens here when whatever we're measuring breaks the beam? This is a 3.5-inch floppy drive. Basically, we had 2 light sources on it. We had one that would tell us if the disc was inserted, and then we had another one. You can look, there's a little switch on the side right here that you could open up a little hole. This is the way we could write protect the disc. So if we wrote protect it. If we write protected the disc by opening up the little slot, then people couldn't wipe out what you had. And yeah, all your VHS tape, you could take that little tab on the back and do what? Yeah, but you could break it. But if you bought one that was pre-recorded, if you wanted to record over, same thing. Here, what you would do is the ones that they would sell you, the tab wouldn't be in there; it would be open up all the time. But if you wanted to write on it, you could do what? You take a piece of tape and cover up the logo. Not transparent. So this is a type we call a through the beam. That's what I learned it at. When we look at these supplements, they're going to call this a direct scan. So we have 2 items. We have 2 parts. We have one that's going to transmit light. So it's just going to be a light source. And then we're going to have a receiver, right? That receives the light. This is definitely going to be electronic. Normally we use LEDs. Now we don't use lights. The first time we ran into these at US Steel, it was actually just incandescent light bulbs. So once in a while they would burn out. That would give you problems. Usually they can be infrared, which means you can't see them, or they're going to be red. Most of them I've seen is red. And so these guys right here, and of course what's going to happen, how these work. So what these guys are going to work is, the way they're going to work, is that whatever we're going to detect, we're going to do what? We're going to move through this and it breaks the beam. So the output of these are going to start off what? True means no object. And then then when they go false, it means there's an object present. So the biggest problem we have with these, of course, is alignment. Is your transmitter and your receiver has to be aligned real well, right? You understand if they get off a little bit, that gives you a problem. So something comes on and knocks your little mount off there. So usually they're mounted on some type of mount if you move around. Very reliable, and they have a pretty good distance range on too. We had one out of U.S. Steel, but it worked on a spotlight. That thing must have went, good gracious, probably around 300 feet. What it was in there, and it was infrared. We had a problem out there where they had to wire where they kept the line crew. So U.S. Steel does a lot of their electrical work out there. Everything out on the plant was done by the line crew. So outbound power didn't come into the plant. And then they had a yard out there that was fenced in, and it had all their big spools of wire out there. Well, somebody came along and figured out they came in there and got into that thing, and they put up a cable to a big old spool of wire, and then they pulled it and ran it out to the corner where the chain is, and they ran it over there, and they came out there at night and hooked a rope onto it and pulled it out. That whole rope pulled it out, and they rolled it off the side of the road over there. What they did was they come out at night and they cut off links and they fell apart. So they came in there and guarded it with these that you could not see. So that way, if somebody came into the yard and got over there with the wire was triggered the police department out there, and they'd come out. But yeah, I don't know if they ever found the guy who did it or not. Now they've got that road closed off. It used to come off of the road that goes over to Pleasant Grove. I don't know what that. And then you could turn off right, and that's the way I used to go to park. This is another one that we call a retro reflector. Everybody see how this works? We have several of these over on our manufacturing line that I showed y'all the other day. We see retro reflectors on stop signs. A lot of our street signs have retro reflectors. We have retro reflectors in the stripes. A lot of the stripes on the road, we have retro reflectors on there. And what's nice about them is you don't have to be perfectly aligned, right? They try to reflect back to the source. Are we okay? Yeah, but there's a viewable angle. You know, it's just like your TV. If you get right up against your TV and try to look at it this direction right here, you can't see anything. Even your phone. So if you tilt your phone at an angle, you cannot see it because the way these LED screens work is they shoot a beam through a little tube, and then the tube has got a color lens on it. And anytime even on traffic lights, they'll put the lights in the tube, so you can't see it from the side. So these guys do have an angle. They will not reflect at an infinite angle. So I don't know what it is, but you can probably look it up. Yeah. Then the last one we have is what we call a diffuse. This probably has the shortest range. So what we do here is we have the transmitter and receiver. So this one, let's go back. So no object. The output would be true. Here, an object, the output would be what? So you're going to have to figure out what you're going to use that contact, right? Whether you're going if it's a normally open and you need a normally closed and all you got is a normally open, what are you going to do? In the control system, PLC is no big deal. In the control system, you're normally closed when the object is. You need that normally closed when the object is present. This is normally open when the object is present. So here's my solid state. And then, of course, it's a 3-wire sensor. So we'd have this running over here. I would take my output and I would move it into this amazing thing called a control relay. Now, not only out of control relay, I can get normally closed contacts. I can also get normally open contacts. I can get this. So I can have this contact now. I can write it out. We don't worry about that. Somebody said we just change it over. Using an example of open. So a diffuse sensor, what we do on a diffuse sensor is we shoot the beam out, then we depend on the light that's reflected back. So what problems would we have with these guys? The through the beam and also the spectral reflective light. So all those reflectors don't work. You know, we've seen that happen. Killed a ladle full of steel, and it hit all this electrical conduit. It just did what to it. Just wiped it out. Bob Silver, you steel was out for a while because they actually steel. That was interesting. And they had to come back and rewire that. But yeah, the reflector, you know, it don't have to be powered. It don't have to work, but somebody can wipe it out. Just take a wipe the sensor. The problem here is that we can't use this to detect items that are transparent, right? On something. So that would be one advantage. The other disadvantage is that if you're in a dirty environment, not even an extremely dirty environment, you're going to have to retro. The guys in Brooklyn, he said that's one of the things we have to do. I forgot how often it is. Go out and do a lot. I mean, all these optical sensors, right? Even though a company is clean as Brooklyn is, you know, there's still a lot of oil and stuff. So this guy right here, we're literally bouncing off the object itself. So here, depending on the amount of light. So this guy, the object closer it has to be to the sensor, right? And of course, the light of the object would receive. So this guy would have problem sensing with the. So a lot of our sensors we have on the Cessna line. We have 3 different colors over there. We have black, we have red, and then we have chrome, right? The chrome and the red are assembled exactly the same. The black is assembled different. So what they do is they have what they use a diffuse sensor, and we adjust it. We have the ability to set the threshold so it don't go to true when it sees the white, when it sees the black. And now your robot will know which string is in there. It'll know what piston strings are same pistons and everything else going on. So we can literally use this to detect different color objects. Not meaning using between 2 or 3, right? Understand that? So the darker it is, the closer it's going to have to be, or the less signal we get, and the lighter it is. And then, of course, if that's transparent, there's no way in the world we can see it with a transparent object because the light will just go through it, right, and not reflect back. So there's our 3 optical sensors. So we have a through the beam, which when you look at the right now, the supplement, you're going to hit the direct the supplement part gives you a big discussion. They refer to this as a direct scan, right? Reflected, which is what, and we need to understand when is so through the beam is true, the output will let current go through. There is no object. false or it would block the current load if there is a the retroreflective works exactly the same way. But it's used. If there's an object, it would be true. So no object, let's do this in the same thing, breaking the beam. This guy here would be false. And an object, it'd be true. But every one of them's got little bitty problems because we're dealing with logic, right? Understand? So through the beam, one of these, it usually pops up, but let me bring up my camera again. So I'm going to choose something. Can y'all see this? So a lot of people, we can do a lot of stuff with light, right? You understand? Now what you would probably notice, if we can see it, is every button generates a different pattern. So in each pattern, your TV would pick it up for what? Increasing the volume or changing the channels. So infrared, well, just because you can't see the light, and I've had people do that, where they go there on these sensors, and they don't see the light, and they think it's bad. The problem is, it's not, it's infrared, right? This is why, so you see it through the thing every once in a while when somebody stands in front of you or channel. By the way, the first one, my uncle, he was always getting the first stuff. And the first remote he had little tuning forks in it. And every time you click something, it would strike a different tuning fork. And then the TV actually did what? Picked that up. And then the next one, the remotes were wired. So you had a wire running from your what? From your TV with your remote. Of course, now we use these optical ones. Then we have what we call a definite reflective. Forgot about this guy. Diffused definite reflection. It looks at a distance. It only detects an object not only if it's there, but it's got to be at a correct distance. So where y'all run into these at? All the time, every day. Anybody got one of these? Just pick it up off the table by a millimeter and it don't work anymore, right? So what's it doing? It's looking for that mouse to not only pick up the grains of the object that you're on, it's also looking for the mouse to be at a certain distance. So definite reflectives are looking for a lot. It's a diffuse detector, but it's looking for the object to be at a distance. Okay, guys, I'll take another break.